All right, we're okay. All right, welcome to Fluids today. Just the quick announcement here at the start on the quiz. So there will be a quiz on Friday. It'll be the first 15-ish minutes of class. If you're going to be here in person, great, show up, take the quiz. If you're going to be here virtually, so if you'll be here virtually, just make sure you let me know so that we can get that straightened out and plan for that accordingly. So quiz on Friday. It's going to be the quiz will be one Reynolds transport theorem problem. It's going to be one of these like momentum problems like we've been doing for the last while. It'll be a single problem. It'll be open notes, homework stuff. So make sure, I guess, you bring that stuff if you want it with you. It's going to be a relatively short amount of time, though, so you won't have time to like flip through everything that we've ever done. So anyway, I guess take that for what it is. It's going to be a single problem. It's not going to be like one of these problems that's, because it's going to be like 15 minutes, I expect you to be able to solve it in that kind of time. So it's not going to be like one of these moving control volumes, crazy, like multiple dimensions, super wild things. It might have multiple dimensions, but it's going to be, relatively speaking, more straightforward than like problem 4 on the last homework, for example. So it'll be relatively straightforward, but it will still require you to think about, okay, what forces are involved and how are these things working? So that's what's happening on Friday. First thing on Friday. Yeah, like I said, so that's first thing on Friday. If you're going to be here virtually, just reach out to me so that we can coordinate that. If you're here in person, we'll see you on Friday. All right, so today what we're going to do is revisit a problem that we already have looked at and kind of ask a new question. And this will really be our last class period talking about these types of problems specifically. Although we'll still use, in some of the next stuff that we do, a lot of the later stuff we do, we'll still use this same kind of concept and idea. But we'll revisit our cart. Everybody remembers this little beautiful cart? Right, we have a little cart. We're going to try to draw it exactly the same. Same problem as before. So this was theta equals 60 degrees. It's this funky looking cart with a snowplow on it. And we have a jet that's shooting, well, let me draw it. It's water, so I'll draw it in blue. Got to take advantage of my colors. And that's going over the cart. Our jet has a velocity in black. Our jet has a velocity, v jet, which we said was 30 meters per second. And it has an area, a jet equals 0.003 meters squared. The cart was rolling around on the ground. It's moving with a velocity, which we'll call u, and that equals the velocity of our reference frame, right? So because we said our reference frame, we're the little person standing here on our cart. So we attached our reference frame to the cart. We said that's like the perspective that we're taking. We're going to look at what our velocities with respect to us standing on this cart. We pinned a set of axes on the cart, which we called X bar and Y bar. To differentiate them from axes, which could be pinned, say, on the ground on Earth, which would just be, we'll call X and Y. Okay, so we can have axes pinned on the Earth or on top of our cart. We said we're gonna take this and we're gonna look at things from the perspective of our little guy standing on the cart. That's where we're gonna measure velocities. That's how we're gonna solve the problem. We wrote the equation for solving this. We wrote F equals, I'll just write the whole equation. V XYZ bar rho dV plus the integral over the control surfaces of V XYZ bar rho dot dA. Okay, so this was, we had in the last class, we said, well, we looked at this problem with our cart accelerating, or our cart moving at 10 meters per second. So we could measure velocities with respect to us sitting on the cart. The jet looked like it was coming at us at 20 meters per second. And that's kind of the perspective that we took. And we said physics doesn't care if our cart's moving or if our cart is stopped. It cares if we have an inertial reference frame. But what happens if we don't have an inertial reference frame? What happens if our cart is accelerating like it actually would in a real problem like this, right? If we had a cart that was, say, stopped and we started shooting water at it, what's going to happen is there's going to be a force exerted on the cart. It's going to speed up and it's going to keep going faster and faster. So what we'll ask today is, how does that work? What happens? So if we have an accelerating reference frame, what happens to this equation? Well, let's look first at the right-hand side. What happens to the right-hand side? So what is the right-hand side? It's measuring the momentum, right? This first term is the momentum inside of the control volume. So the momentum inside of the control volume, again, with respect to our reference frame, is the velocity with respect to that reference frame times the mass. So that works just the same as before. That would be the momentum inside in terms of our reference frame. And this part here is the momentum that's carried into or out of our control volume, right? So fluid's going to be flowing in, fluid's going to be flowing out. It's going at some speed, it has some mass, it carries with it some amount of momentum. This tracks us how much momentum is coming in, how much momentum is leaving. So this part, both of these terms, don't really care if our control volume is stopped, if it's moving, if it's accelerating, whatever is happening, they all work the same. So this whole side works the same with an accelerating CV, just so long as we are measuring velocities with respect to the control volume. So we still, we're still measuring velocities with respect to this control volume, but in that kind of picture of things, like how momentum is flowing in and flowing out and accumulating, that part doesn't actually change. So what does change is the other side of the equation, the left-hand side. So this part now works differently. Okay, so we'll investigate it for a little bit how exactly that part changes. So where did that come from? That came from this, that, right, the momentum, with the change in momentum with time for a system equals F. So F equals ma, right? That's where this comes from. That works for an inertial reference frame. Which is why it worked when things were stationary or when they were moving at a constant velocity, because that works the same in both. It just has to be inertial. If we're no longer inertial, if we are accelerating, it doesn't work quite the same. But we could write that the change in momentum in our new reference frame that is accelerating, XYZ bar dt, that still equals force. Okay, so that works in our new reference frame, but now we need to relate our accelerating to our accelerating reference frame to an inertial reference frame, or to the Earth. So for all of this stuff to work, we basically have to take so our cart, which is accelerating, and relate the acceleration of that reference frame back to something that's not accelerating, back to the Earth. So that's what we're going to do. We're going to take this thing that's accelerating, we're going to relate that acceleration back to the Earth, which is not accelerating. Okay, so that would look like, so our momentum change in our accelerating reference frame is equal to the change in momentum with time in the Earth's reference frame plus the change in momentum with time of the reference frame itself. Right, so again, to rewrite this, or you could think about this, that the velocity in this reference frame equals the velocity with respect to the Earth, XYZ without a bar, plus the velocity of the reference frame itself. Or again, to bring it back to the cart, I know you haven't had a chance to finish copying that, but our cart is moving. So the velocity from standing on the cart, the velocity of what things look like standing on the cart is the velocity of what they look like from the earth plus the velocity that the cart is moving itself. So these two things are kind of mixed, right? That at least kind of makes sense. So this part here is that is equal to the force acting on the object. This other part here is the mass, of our reference frame times the acceleration of our reference frame, right? The change in momentum with time of the reference frame itself. Okay, so we can write that, we can kind of combine all of this stuff together, and what we get is basically the same equation modified for the reference frame acceleration. So I'll write what that is. So it would be something like this: surface forces plus body forces minus the mass of the reference frame times the acceleration of the reference frame equals, and then what we've had before. Velocity, x bar, y bar, z bar, rho volume, plus our control surfaces of v rho dot dA. So the interesting point for this, the force is reduced by mass of the reference frame times the acceleration of the reference frame. So there's kind of this like correction factor. That's like, I think, the best way to think about it. There's like a correction factor where the forces in the system are kind of reduced because of the reference frame acceleration. Right, this is just to be a little bit clear. So A is the reference frame, accel with respect to an inertial. Right, it's the acceleration with respect to Earth, for example. Okay, so there's a lot of cool things that you can do with this. We're not going to do too much with it. We're going to do this one example problem, this cart example problem now, and there's going to be one homework problem where you guys use this, and then we're just going to kind of let it be. So this won't show up again on an exam. It'll only show up on the one homework problem because I don't think it's worth going too in depth with some of the math from this, but I do think the kind of interesting concept is when you're thinking of how like these force balances and stuff work in fluids, it's like a correction factor almost to the forces that are applied. Like an acceleration becomes kind of a correction factor to the forces being applied in the system. That correction factor is the mass times acceleration, the force that's required to yield the acceleration that's seen. So it's kind of a, I don't know, kind of an interesting thing. So, so let's go back to our cart. So for our cart, let's look at the acceleration of our cart from a stop. And we're going to assume like, okay, so no friction or drag. So we're going to let it, it's a perfect cart, like one of those you guys do in physics lab, like the little carts that ride on the track and are super smooth. So, okay, it's one of those carts. And we're shooting it with some water, it's bouncing off of it. So that's going to cause it to, from stop, accelerate, and it's going to end up reaching a maximum speed of the velocity of the jet. So eventually those two would match. So we have no friction, no drag. We're going to look at just the x momentum. And that's because that's the only one that matters for the acceleration in the x direction. So the y momentum is still there, it's still happening, but we don't have to care about it for this particular problem, because that's not leading to an acceleration. We're going to look at uniform flow, and A1 equals A2 equals a jet. So the jets, as it's hitting this slope, it's not slowing down at all. It's staying the same speed. It's a uniform speed, so the areas are going to stay the same as well. So the water shoots off at the same speed. At same speed. Okay, so all right, so let's look at what this would be. So we have the surface forces plus body forces minus the mass of our reference frame times the acceleration of our reference frame equals d of v rho dv plus d a. Oh, the last thing that we're going to say is steady state. So let's start simplifying this initial equation. So the first term to go is the surface forces. So the pressure everywhere is atmospheric pressure or zero gauge pressure, so that term drops out. No body forces in the x direction. So G, no gravity in the x direction. The reference frame is accelerating, so that term stays. This drops out because we have steady state. And then our integral turns into a sum because we have uniform flow. So this okay, so that's all of the simplifications that we're going to be able to do. So we have minus the mass of the reference frame times the acceleration of the reference frame equals the sum over our control surfaces of V XYZ rho V XYZ dot A. Okay, so now let's remind ourselves, we go back to our little cart, remind ourselves where our control volume is specifically. So remember, our control volume is this section here. It has surface 1 and surface 2. Control surface 1 is right where the jet's first hitting and first starting to turn. It's where this momentum changes. Control surface 2 is where it launches off the top surface of the cart. Again, where that momentum change, where the velocity change stops, right? The velocity is not curving anymore. So those are our two control surfaces. We want to look, we'll define a couple variables. So we have to define what's the velocity coming in to control surface 1. What's the velocity leaving control surface 2? What are the areas? So we'll define all of those different quantities. Okay, so some definitions. This is okay, U1. Well, let's expand this a second, and then we'll do our definitions. This should be the acceleration of our reference frame in the x direction, because we only care about x. So just in the x direction. This equals, so now it's U1 rho velocity dotted with the area. So this is going to be U1 dotted with A1. Those are pointing in opposite directions. So that gets a negative sign. U1, or I guess I'll write it this way. V1, A1, the speed, right, at surface 1 times that area, plus U2 rho. Now these are both shooting off the top in the same direction. So V2, A2. Okay. U1, that's the x velocity at side 1. So that's going to be how fast is the cart moving. So how fast the jet coming at us minus how fast the cart is moving. So this is equal to V jet minus U cart. Or we'll just to simplify my notation, we'll just call this VJ minus capital U C. Okay, instead of writing jet and cart every time in subscripts. So that's the x velocity at side 1. The speed of the jet, V1 equals V2 equals the same thing, V jet minus UC. So that's the speed in this reference frame. So the speed is going to be the same at both sides, but the different one is U2. So the x speed, when it's shooting off at this 60-degree angle, is going to be the speed times cosine of the angle. So this will be Vj minus UC cosine theta. Okay. Then the last thing, A1 would be equal to A2, should be equal to A jet. But because they're all A's, we'll just call it A. Because those are all going to be the same value for this particular problem. Okay, so let's, again, keep working a little bit on the right-hand side. So we're going to take all of this stuff and simplify that right-hand side with it. So the mass of our reference frame times the acceleration of the reference frame in the x direction, which is the one that we care about, is equal to, so this is the velocity of our jet minus the speed of our cart times density. Okay, we get a negative sign, so let's put a negative sign. I'll put my negative up front. Negative, I'll make it big so that I don't forget it. I think I missed 2 negative signs in the last class. It was great. Okay, so I'll try to remember the negative. And then this is Vj minus the velocity of our cart times A plus, okay, same kind of thing. Velocity of the jet minus the speed of the cart times cosine of theta times density, and then minus speed of the cart times A. All right, so we can simplify things quite a bit from here because they all have a lot of the same terms. They all have rho, they all have A, and they all have the velocity of the jet minus the speed of the cart squared. Right? They all have 2 of those. The only difference is the first term has a -1 in it, and the second term has a cosine theta. So we can write minus mass of the reference frame, A reference frame X equals cosine theta minus 1 times, okay, rho J minus UC squared A. Okay. Just so that I don't mess up so much on signs, we're going to flip the sign on both sides, multiply both sides by -1, so that the mass of the reference frame, acceleration, reference frame, x equals 1 minus cosine theta rho. Okay, so flip the sign so that I don't screw up more than I have to. Okay, so now we have to ask ourselves, okay, so the right-hand side, we pretty much got that. The left-hand side, what do we do with that? So we have this mass of the cart, mass of the reference frame, that's the mass of the cart. So mass the acceleration of the reference frame in the x direction, right? Our reference frame, we are, okay, let's go back up here. We are standing on the cart, right? This is us standing on the cart. So how are we accelerating? Well, we're experiencing an acceleration. The reference frame is experiencing an acceleration, which is the change in the speed of the cart with time, right? How does this cart, it's going to be stopped initially, and it's going to end up going faster and faster and faster and faster. So the acceleration that we're experiencing is the acceleration of the cart. That's the acceleration of the reference frame. So we can write that as That is the change in speed of the cart with time. That's all that acceleration is. So we have the mass of the cart times the change in speed of the cart with time equals 1 minus cosine theta rho the jet minus u cart squared a. So we want to integrate this to be able to figure out how this actually works with time. So we need to separate variables, get the, right, we have a speed of the cart on both sides of the equation. Everything else is a constant. So we want to get the speed of the cart onto one side and all the time stuff on the other side. So this would be 1 over EJ minus UC squared DUC equals, and then we have a whole bunch of constants. So this would be 1 minus cosine theta rho A over mass cart times dt. So just because I'm going to get sick of writing these constants over and over again, we will simplify them. So we'll let that all equal b. So that we have 1 over c squared d u equals b dt, where b is just this grouping of constants. So now we have to think a little bit how we want to integrate. So we want to integrate both sides. The right-hand side is obviously really easy. The left-hand side feels a little bit weird, but we can do kind of an easy u substitution. So I'm going to do it, I guess, a little bit hand-wavy, but hopefully you can follow. So v jet is a constant, right? So so the change in speed of the cart, a differential change in speed of the cart must be equal to BUC minus BJ, right? If you look at that, does that make you happy? Okay, why is this the case? This is, so if the speed of the cart changed 0.1 meters per second, then that difference also changed by 0.1 meters per second. Would you agree with that? Okay, so if we see any change in the speed of the cart, right, the only change in this difference is caused by a change in the speed of the cart. That's basically what we're saying. Because the jet is just a constant speed. Right? Does this pass the math smell test? Should. It's a little sneaky, but or we could write this equals negative d dj minus uc. Okay, it's basically like a u substitution. I'm just not defining something as u. That's all that I'm essentially doing. Then we can write 1 over UC squared B, this would be minus is equal to B dt. All right, so then we can integrate. So we're going to integrate from stopped to whatever speed we happen to be going. So integrate up, up to some velocity and some corresponding time. So we're going to integrate from 0 to whatever the velocity and time happen to be at that point. So we'll integrate both sides. So the integral from 0 to our velocity of -1 over Bj minus, you see that quantity squared d to c equals b times t. Right, that second side is really easy. This integral, it feels a little bit weird, but it's actually not too hard. This is, right, right, because we're doing this is why we have like d v jet minus u cart, that quantity. Right, so then we have that quantity squared, so minus the quantity to the -2. If we do the integral, this is minus, or this becomes, rather, Vj minus uc to the -1. Right, if we took the differential of this, the -1 would come down to the front, and then we'd get a -2 up top, evaluated from 0 to uc equals b times t. So if we evaluate this, this gives us 1 over velocity of the jet minus the speed of the cart minus 1 over the velocity of the jet minus 0 equals bt, or so just b jet minus u c minus 1 over b jet equals b t. Then we have to do a little bit of algebra to solve for our speed, the speed of our cart uc. So that's fairly straightforward. So we can get, right, 1 over b j minus uc equals bt plus 1 over velocity of our jet. And then we can flip both sides, multiply both sides, or take both sides to the -1 power. So that would be, well, we would get, sorry, rather, what would we do? We would get a common denominator. We multiply both sides by how would we do that? Algebra is hard. Yeah, so you'd have to separate, you have to get this out of there, but how would that work? Because you'd raise both sides to the -1 power. So that would give you Vj minus uc plus 1 over to the -1. I'm getting sign errors, minus. Is that right? That's right. So then UC would be equal to EJ. This doesn't seem, yeah, okay, that seems right. BT, I guess this, let's write this a little bit differently. So this would be 1 over BT plus 1 over the velocity of the jet. Yeah, I think that's right. Because that, so at time zero, what would happen? So at time zero, the right-hand fraction would be the velocity of the jet, because you'd have 0 plus 1 over the velocity of the jet, 1 over that, so that would be just velocity of the jet minus the velocity of the jet, so your speed would be 0. And at time infinity, when t goes to infinity, that fraction on the right goes to 0 because you have an infinity on the bottom. So then your speed at time infinity is just the speed of the jet. So you start out at 0 and accelerate up to a maximum speed, which is the speed of the jet. So, yeah. Okay, yeah, that all looks right. So the kind of cool thing is you can use this to look at like acceleration of bodies because of fluid forces. If you wanted to figure out like how an airplane accelerates at takeoff, you could use this, or a rocket ship or something like that. You could use some of the same types of thought processes, how something is changing speed when because of some of these fluid forces. We're not going to do too, as I said before, we're not going to do too much else with that. I think one of the kind of key interesting thought things to take away is really that acceleration is kind of just like a correction factor to the forces that are happening in the system. But if you allow your body to you allow your reference frame to accelerate, that gives like a correction factor to the forces that are experienced because of the fluid motion. So that's where that shows up. Like I said, you'll get a chance on the homework to play around a little bit with this. Where we'll pick up on class on Friday, so we'll have the quiz, and then we're going to sort of drop Reynolds transport theorem, and I say that sort of because we're going to immediately pick it back up just in a different context. And say, so we have, with Reynolds transport theorem, this gives us an idea of how fluids respond to forces. But as of now, we have no idea how flow actually works. Like, in detail, right? If I said, I mean, every time that we've had any problem where we've looked at fluid flow, like velocity profiles and stuff, I've always had to just tell you what it is, right? What is the velocity profile inside of a pipe? I just had to tell you that. What is the velocity profile of like a jet of water hitting a wall? I had to tell you that. So anytime we've had to actually look at what fluid velocities, like how they work, we've just like taken it on faith. We're gonna, okay, say how can we then like take some of these systems, just like a fluid flowing, use some of these same concepts of Reynolds transport theorem and get to a better like point-by-point description of how fluid flow actually works in response to forces. Not just how fluids can exert forces on objects, but like how fluids actually respond to forces in like a point-by-point description. So that's where we're going to next. I think it's kind of interesting and fun to see how we can build some of the we're going to build really ugly differential equations, but kind of do it from the ground up. So I think it'll be, I think it's kind of interesting. That will be next time on Friday. This is the end of Wednesday. So remember, there's a quiz on Friday. If you're not going to be here in person, just shoot me an email and let me know so we can schedule that. All right, take care, everybody.